The Moon is not behaving the way it should. Not in a dramatic sense. It is not moving in the wrong orbit, not going through phases in the wrong sequence, not demonstrating anything that violates the laws of physics in any fundamental way, but in a subtler and in some respects more unsettling sense. Because when you begin assembling the specific observational data accumulated over the past several decades, a picture starts to emerge that our current models do not fully explain. The Moon is releasing heat from its interior in amounts that do not match what our models predicted. The Moon has magnetic anomalies, regions where its local magnetic field is significantly stronger than the surroundings, whose origin remains actively debated. The Moon contains water, not only in the permanently shadowed polar craters where it was expected, but on the sunlit surface where by all calculations it should not persist. The Moon is shrinking, its crust forming young scarps and wrinkles indicating ongoing compression of the interior that is more active than standard models predicted. The Moon shakes. Moonquakes continue occurring at depths and for reasons that do not fit neatly into a simple picture of a geologically dead world. And perhaps most strangely, the Moon shows signs of recent volcanic activity. Not ancient, recent, in geological terms. Tonight we are going to go through all of this, not to offer sensational explanations. The real science here is interesting enough without exaggeration, but to honestly lay out what the data says, what the models predict, and where a gap exists between them. Because that gap, the space between what we expected from the Moon and what the Moon is actually doing, is one of the most actively investigated questions in planetary science right now. Before we begin, if you put this on because the night is long and you need something to settle into, stay. The Moon is strange. This is worth paying attention to. Let us start with the most fundamental strangeness, with a question that seems like it should have been resolved long ago, but that in fact remains one of the active discussions in lunar science. Is the Moon actually geologically dead? The standard answer you find in most textbooks is yes. The Moon is too small to retain enough internal heat to sustain geological activity. Its interior cooled down. Volcanism ended approximately 3 billion years ago. The Moon is a cold, dead world, its past activity recorded in the basaltic plains of the Maria, but long since stopped. This was a reasonable model. It is based on real physics. The Moon has a mass approximately 81 times less than Earth's. Smaller bodies cool faster because they have a higher ratio of surface area to volume. Heat from the interior has a shorter path to the surface. Mars, larger than the Moon by roughly a factor of 9 in mass, already shows signs of significantly more advanced geological cooling than Earth. The Moon is smaller still, and should have cooled even earlier. But the data that has accumulated since the 1960s, beginning with the Apollo missions and continuing to the present, paints a more complicated picture. Start with moonquakes. The seismometers placed on the lunar surface by Apollo astronauts, specifically at the Apollo 11, 12, 14 and 16 landing sites, operated from 1969 to 1977 and recorded thousands of lunar seismic events. This data became one of the most scientifically valuable legacies of Apollo. It gave us the first direct probe of the Moon's interior structure. The moonquakes turned out to be significantly stranger than expected. Earth's earthquakes occur through several mechanisms: tectonic plate motion, volcanic activity, collapse, and the overwhelming majority occur in the upper few hundred kilometers of crust and mantle. The moonquakes divided into several distinct categories, each with its own characteristics. Shallow moonquakes, occurring at small depths from the surface, turned out to be associated with thermal stress. The Moon heats up in daytime and cools at night in extreme ranges. Surface temperatures reach plus 127 degrees Celsius in daylight and minus 173 degrees at night. And this thermal expansion and contraction produces small surface cracks and seismic events. This is understandable and expected. Deep moonquakes, occurring at depths of 700 to 1,200 kilometers, turned out to be more puzzling. These deep events occur in regular clusters, correlated with Earth's tidal forces. They are most common when the Moon is closest to Earth on its slightly elliptical orbit. This suggests that Earth's tidal stress is triggering these events, that the deep lunar mantle is still sufficiently plastic to respond to tidal deformations. Dead, cold, solid bodies do not do this in this way. But the most baffling category turned out to be the so-called shallow moonquakes, occurring at depths of approximately 50 to 200 kilometers, significantly more powerful than the deep events, reaching magnitudes of 5.5 in intensity. They do not correspond cleanly to either tidal triggering or thermal stress. Their origin remains uncertain, and they suggest that the upper mantle of the Moon is more active than the standard model of a cooled-down world predicted. The Apollo seismic data also gave us information about the internal structure of the Moon, through how seismic waves propagate through its interior. The results showed a crust approximately 30 to 40 kilometers thick on the near side and 50 to 60 kilometers on the far side. This asymmetry is one aspect of the lunar dichotomy that remains partially unexplained. Beneath the crust, a mantle. Beneath the mantle, a core. And here is what is strange about the core. The Apollo data suggested a small iron core, possibly 300 to 400 kilometers in radius. This itself was surprising, because standard models of the Moon's formation from a giant impact predicted a very small core, or none at all, because the proposed impactor struck at an angle that would have ejected predominantly mantle material into the proto-lunar disk. A small but significant iron core, real, measurable, is evidence of a formation history more complex than the simple giant impact model. Later data from the Grail mission, two small NASA spacecraft that flew in tight formation around the Moon in 2011 to 2012, measuring the lunar gravitational field with unprecedented precision, refined our picture of the lunar interior. Grail showed that the Moon's crust is more porous than expected, densely riddled with fractures and faults from ancient impact bombardment. This result changed our estimates of the average density of the crust and its composition. Let us now talk about heat flow, about what Apollo data and more recent missions tell us about how much heat the Moon is releasing from its interior, and why that result turned out to be more complicated than expected. Apollo 15 and Apollo 17 astronauts installed heat flow probes, instruments measuring the rate at which heat conducts from the lunar subsurface to the surface. These are direct measurements of the Moon's internal thermal activity. They tell us how much heat is coming out of the lunar crust at a given location. The results were surprising. At the Apollo 15 site, the heat flow measured approximately 21 milliwatts per square meter. At the Apollo 17 site, approximately 16 milliwatts per square meter. Both values were higher than standard models of lunar thermal cooling predicted. But there is a complication. Both Apollo landing sites where heat flow measurements were made are located near Oceanus Procellarum, the large dark volcanic plain on the near side of the Moon. This region is known as the creep terrain, a region unusually enriched in potassium K, rare earth elements Re, and phosphorus P, as well as the heat-producing radioactive elements, uranium, thorium, and potassium-40. The concentration of heat-producing radioactive elements in this region is significantly higher than for the Moon on average. This raises the question, do the Apollo heat flow measurements represent typical conditions for the whole Moon, or are they specific to the anomalously Care-EP-rich region where the spacecraft landed? The answer has significant consequences for our understanding of lunar thermal evolution. If the Care-EP terrain is atypical, and it is by its composition, then the global heat flow of the Moon may be lower than the measured values suggest. Standard models may be correct, and the anomalous measurements reflect local geology rather than a global anomaly. But if the Apollo measurements are representative of wider areas, if the Moon's heat flow in general is higher than standard predictions, then our models of lunar cooling are wrong, and the Moon has retained significantly more internal heat than they predicted. Resolving this dilemma requires heat flow measurements from different locations, especially from the far side of the Moon and away from the creep terrain. This is part of the scientific program of Chang'e 4, the Chinese lander operating on the lunar far side since January 2019. Preliminary results are beginning to emerge, and their analysis is ongoing. Let us talk about water, because the discovery of water on the Moon is one of the most significant and least fully understood discoveries in lunar science over the past 2 decades. For a long time, the Moon was considered anhydrous, completely devoid of water. Apollo samples were highly dry, indicating that the high-temperature formation of the Moon in a giant impact had evaporated any water that might have been present. The lunar surface is bombarded by solar ultraviolet and solar wind that destroy water molecules. The standard picture was a dry world. This picture began to change in the 1990s. Radar observations from the Clementine mission suggested the possible presence of ice in permanently shadowed craters near the lunar poles, regions where temperatures never rise above approximately -163 degrees Celsius, cold enough for ice to be stable for billions of years. Subsequent observations from lunar prospector using a neutron spectrometer detected elevated hydrogen content in polar regions, consistent with the presence of water. Definitive confirmation came in 2009 from the LCROSS experiment, the Lunar Crater Observation and Sensing Satellite. A 2,000-kilogram rocket stage was deliberately crashed into the permanently shadowed crater Cabeus near the lunar South Pole. The impact ejected a plume of material more than 4 kilometers high, which the trailing analysis spacecraft flew through and found to contain water. Approximately 155 kilograms of ice was detected in the ejected material. This was direct confirmation of water presence in lunar polar regions. Since then, the characterization of ice in permanently shadowed craters has significantly improved. Data from the Lunar Reconnaissance Orbiter has confirmed ice presence through neutron and optical observations. India's Chandrayaan-1 mission detected hydroxyl OH compounds across the sunlit lunar surface using infrared spectroscopy, an unexpected result indicating that water, or hydroxyl, is more widely distributed on the Moon than only in polar shadows. The most surprising result was the detection of water on the sunlit lunar surface, confirmed in 2020 by observations from the Stratospheric Observatory for Infrared Astronomy, SOFIA. SOFIA's infrared spectroscopy detected the characteristic molecular absorption band of water at 6 micrometers, unambiguously identifying H2O rather than just hydroxyl OH in the Clavius crater region near the lunar South Pole on sun-illuminated surfaces. This is remarkable. How can water persist on a sun-illuminated surface where ultraviolet radiation and solar wind should rapidly destroy it. Several mechanisms have been proposed. One suggests that water may be trapped in microscopic glass beads, tiny spheres of glass created by meteorite impacts, which protect it from photolysis. Another suggests that water is continuously being created through the interaction of solar wind with the lunar regolith, hydrogen ions from the solar wind implanting into oxygen-bearing surface minerals and forming hydroxyl and water. Yet another suggests that water migrates across the surface from illuminated to shadowed regions through sequential molecular hopping. The actual distribution of water across the Moon, how much there is, exactly where it is located, what form it exists in, how it got there, remains one of the most actively investigated questions in lunar science. Artemis 3 and subsequent planned landings near the South Pole are specifically directed at this investigation, because understanding the availability of lunar water is critical both for science and for future plans for using lunar resources. Let us now talk about lunar swirls, one of the most visually striking and least understood features of the lunar surface. Lunar swirls are bright, sinuous patterns on the lunar surface, existing in hundreds of locations across the Moon. Some are small, only a few kilometers across. Some are enormous. The most famous swirl, Rhina Gamma, located in Oceanus Procellarum, extends approximately 70 kilometers and is visible even through a small amateur telescope as a pale, sinuous marking on the dark volcanic plain. What makes swirls unusual is three specific properties that exist together and are not easily explained by a single, simple model. First, they are always associated with local magnetic anomalies. Where there is a swirl, there is an unusually strong local magnetic field. This relationship is one-to-one. Every swirl correlates with a magnetic anomaly. Every major magnetic anomaly correlates with a swirl. Second, they are optically brighter than the surrounding surface, meaning they reflect more sunlight. This is related to the fact that they contain finer, more immature regolith grains, regolith that has been less exposed to solar wind and cosmic rays. The regions surrounding swirls are typically darker and more space-weathered. Third, they often have a specific pattern, a bright center with alternating bright and dark lanes radiating outward, that suggests the surface material has been somehow redistributed or differentially protected. What produces lunar swirls? The leading hypothesis is that local magnetic fields partially deflect the solar wind, the stream of charged particles, away from the surface. Surfaces shielded from the solar wind accumulate less space weathering, the process by which solar wind bombardment gradually darkens lunar regolith over time. The brightness of swirls is therefore a consequence of their reduced exposure to solar wind rather than a fundamentally different mineralogy. But the origin of the magnetic anomalies themselves is less clear. The Moon today has no global magnetic field. Unlike Earth, with its powerful dipole field generated by the fluid outer core, the Moon generates little or no global field today. Its current weak external field is entirely induced from the solar wind and Earth's magnetic field when the Moon is in Earth's magnetosphere. But Apollo samples showed that some lunar rocks are magnetized. They carry a permanent magnetization, indicating that they solidified in the presence of a magnetic field. This suggests that the Moon had a dynamo, a fluid conducting core producing a magnetic field in its past. When this dynamo operated and when it ceased are subjects of active research. The most recent data suggests that the lunar dynamo may have been active until approximately 1 to 2 billion years ago, significantly later than most early models thought. Despite this past dynamo, the origin of the specific localized anomalies of the swirls remains debated. One scenario suggests they formed from antipodal impact effects. When a large meteorite strikes one location, the shock waves focus on the opposite side of the Moon and can magnetize rocks there. Many large magnetic anomalies are indeed located approximately opposite large impact basins. Another scenario suggests that magnetization occurred when comets, carrying magnetized material or producing temporary plasma fields on impact, interacted with the lunar surface. Neither scenario fully explains all observed characteristics of the swirls. They remain among the most enigmatic features of the lunar surface. Let us now talk about lunar transient phenomena, the temporary flashes and glows that have been observed on the lunar surface for centuries and that continue to puzzle researchers. Lunar transient phenomena, LTP, are short-duration optical changes observed on the lunar surface. They include flashes, obscurations, color changes, and movements, sometimes observed lasting from seconds to hours. Reports of these phenomena date back centuries. Medieval monks recorded bright flashes. Astronomers of the 19th and 20th centuries reported anomalous observations in certain craters, especially in the crater Aristarchus. Serious documentation of LTP began in the 1960s. NASA compiled a catalogue of more than 300 LTP reports by 1968. Observations continued after Apollo, with professional and amateur astronomers reporting transient events with increasing frequency as the astronomical network monitoring the Moon improved. Several explanations have been proposed. The most widely accepted is meteorite impacts. The lunar surface is continuously bombarded by meteorites of all sizes, from submicron dust to occasional larger objects. Impacts produce flashes visible from Earth, particularly during meteor showers when the background impact rate is higher. Professional observing campaigns have successfully recorded visible impact flashes correlated with meteor showers, confirming that some LTP are unambiguously impact flashes. But meteorite impacts cannot easily explain all the reported characteristics of LTP. Some events last minutes or longer, significantly longer than expected for an impact event. Some show repetition at the same locations, especially in Aristarchus and Alphonsus, which is unusual if events were random impacts. Some involve color changes, reddening or brightness variations that do not match the expected signature of an impact flash. Alternative explanations include outgassing, degassing from the lunar interior. If the Moon retains some volatile materials in its mantle or crust, argon, carbon dioxide, other gases, periodic tectonic events or thermal cracking may open vents that allow gas to escape. The interaction of escaping gas with solar wind and surface electrostatic fields could produce visible glows. This scenario received partial support from the Apollo 17 detection of argon-40 streams emanating from the lunar surface at specific locations, correlating with tectonic faults. Argon-40 is a product of radioactive decay of potassium-40 in the lunar mantle. Its presence in gas streams suggests that some degassing from the interior is occurring. Electrostatic mechanisms have also been proposed. The lunar surface accumulates electrostatic charges from solar wind interactions, and during solar events, or when the Moon passes through Earth's magnetospheric tail, the charging conditions change. Electrostatic discharges a kind of lunar lightning, may occur that produce visible flashes or loft dust, creating observable obscurations. None of these explanations is fully satisfactory for all reported events. Likely different mechanisms explain different classes of LTP. Impacts explain some, degassing others, electrostatics others still. But the fact that no single explanation covers the full spectrum of reported events suggests that our understanding of active processes on the lunar surface is incomplete. Modern LTP monitoring networks, including professional telescopic observations specifically directed at the Moon during meteor showers, and the NE-LEOT monitoring system operated by ESA on the 1.2-metre telescope at the Cryonery Observatory in Greece, are systematically cataloguing impact flashes and other events. This data is gradually separating the various classes of phenomena and constraining their occurrence rates. Important work for understanding both the current state of the lunar surface and the hazards for future surface operations. Let us now talk about what may be the most striking recent discovery in lunar science: the evidence for recent geological activity. Not ancient, recent. In 2014, a team of researchers published an analysis of lunar reconnaissance orbiter images showing young lunar scarps, small, steep cliffs in the crust. These scarps, called lobate scarps, form when the crust compresses and one section thrusts over another. They are present across the entire Moon in numbers exceeding 1,000 identified to date. What made these scarps particularly significant was their relative youth. Lunar surfaces are dated by crater counting. The more craters per unit area, the older the surface. The scarps have very small numbers of craters, some virtually none, indicating that they formed very recently. In geological terms, within the past few 100 million years. Some may be significantly younger, within the past few tens of millions of years. For a planet 4.5 billion years old, a few 100 million years is recent. This suggests that the Moon is geologically active in the current epoch, not at the level of Earth with its plate tectonics or Io with its volcanism, but active in the sense of ongoing tectonic deformation occurring as the slowly cooling interior contracts. In 2019, even more striking data emerged. Analysis of Apollo seismic data, this time reread with modern processing algorithms far superior to what was available in the 1970s, showed that a number of recorded shallow moonquakes occurred near young scarps. In other words, scarps formed by tectonic compression are still seismically active. The Moon is creating new faults and moving along existing ones right now. Furthermore, geological analysis of some scarps showed that they disrupt, overlie, or cut through regolith deposits that accumulated over the past few million years. This means scarp formation has been ongoing during this period. The Moon has gotten smaller, its circumference reduced by approximately 50 meters over the past few 100 million years, as the crust wrinkled during cooling. This is not catastrophic change. 50 meters in circumference is an insignificant change for a body 3,474 kilometers in diameter. But it is a real, measurable, ongoing change. The Moon is not a static, dead world that stopped changing billions of years ago. It is slowly contracting. Its crust is slowly deforming. This deformation produces moonquakes. These moonquakes are still occurring. Let us now talk about the evidence for recent volcanism, because this is one of the most debated claims in lunar planetary science, and it is important to lay it out precisely. The standard model says that lunar volcanism essentially ended approximately 3 billion years ago. The large basaltic Maria plains, the dark regions visible from Earth, formed between roughly 4 and 3 billion years ago. After that, the Moon cooled too much for large-scale volcanism. But evidence has complicated this picture. Beginning with analysis of data from various lunar missions, particularly Lunar Reconnaissance Orbiter, Kaguya, and Chandrayaan-1 data, researchers have identified features called irregular mare patches, or IMPs. These are small, typically 100 meters to a few kilometers across, dome-like structures that do not fit the category of impact craters and have mineralogy consistent with volcanic glass or lava. Crater counting on some IMPs suggests they formed significantly after 3 billion years ago, possibly as recently as 100 to 50 million years ago. If these datings are correct, it means that volcanism continued on the Moon significantly longer than the standard model predicted. But this interpretation remains contested. Crater counting dating has substantial uncertainties, especially for young surfaces where small numbers of craters produce large statistical errors. Small numbers of craters can mean a young surface, or simply a surface that, for reasons related to its specific location or material properties, has been struck less than average. Some researchers argue that IMPs are small volcanic features that formed within the normal lunar volcanic period, but are just small and therefore accumulated fewer craters. Others argue that the crater counting data is compelling and supports genuinely young volcanism. Samples from potential IMP sites or near them would be scientifically valuable, since radiometric dating of samples is significantly more precise than crater counting. Artemis missions planned near the lunar South Pole will not specifically target IMPs, but continuing lunar exploration may eventually include visits to these potentially young volcanic features. A parallel line of evidence points to recent volcanism through chemistry. Lunar orbital probes have detected radon, a gaseous radioactive element with a half-life of 3.8 days, produced from the decay of uranium and thorium, emanating from certain locations on the lunar surface. Since radon has no chemical reason to accumulate in surface regolith, its presence indicates transport of gas from deeper regions, through vents or fractures, that may be associated with residual thermal activity. Let us now talk about the lunar plasma environment, about the strange and poorly understood space immediately above the lunar surface that has been getting better characterized and that has turned out to be far more dynamic than expected. The lunar surface exists in continuous interaction with the solar wind and solar radiation. On the sunlit side, ultraviolet radiation from the sun knocks electrons out of surface materials, a process called the photoelectric effect, creating a positively charged surface layer. On the dark side, the surface accumulates negative charge from solar wind electrons. At the terminator, the boundary between the sunlit and dark sides, these contrasting charging regimes meet. The result is an electrically active surface. Regolith above the surface can be electrostatically levitated, dust grains charged by the surface being repelled from it. Apollo astronauts reported seeing a glow near the horizon, particularly near the terminator, that may have been sunlight scattered by suspended dust lifted by electrostatic forces. This glow was sketched by Apollo astronauts and has been discussed in the scientific literature as possible evidence of a dust exosphere. The Moon also interacts with Earth's magnetosphere. For approximately 5 to 6 days each month, The Moon passes through Earth's magnetotail, the extended region of Earth's magnetic field on the night side of the planet. During this passage, the solar wind is partially excluded and the Moon's charging environment changes dramatically. The plasma environment in the magnetotail is different from the open solar wind. Different particle populations, different energies, different densities. The transition in and out of Earth's magnetotail produces measurable changes in the lunar surface charging state. These changes can trigger dust lofting and may contribute to some of the transient phenomena observed from Earth. The specific dynamics of this interaction, how lunar surface charging responds to the changing plasma environment as the Moon enters and exits the magnetotail, is an active research area. The Artemis mission, 2 spacecraft repurposed from the Themis Earth magnetosphere mission, has been studying the lunar plasma environment in detail since 2011. Artemis measurements have characterized the solar wind interaction with the lunar magnetic anomalies, the charging of the lunar surface in different plasma environments, and the dynamics of the lunar wake, the cavity in the solar wind plasma downstream of the Moon. These measurements have revealed that the lunar plasma environment is more structured and more dynamic than simple models predicted. Let us now talk about the lunar interior in more detail, about what we know and do not know about the structure of the Moon's deep interior, and why this remains one of the key uncertainties in lunar science. The Apollo seismic network gave us the first constraints on lunar interior structure, but the network had limitations. It consisted of only 4 seismometers, all located on the near side of the Moon within a relatively small geographic area. The limited geometry of the network meant that seismic waves from events on the far side of the Moon or deep in the interior were less well constrained. The lunar core remains particularly uncertain. Multiple analysis approaches applied to the Apollo seismic data have given slightly different results for the core's size and structure. The most detailed analysis, using modern waveform inversion techniques applied to the Apollo data, suggests the Moon has a solid inner core, approximately 240 kilometers in radius, a fluid outer core, approximately 300 to 350 kilometers in radius, and a partially molten zone at the base of the mantle, approximately 500 kilometers thick. This structure is similar in broad outline to Earth's layered core, but smaller and less well characterized. The existence of a currently fluid outer core is significant. A fluid metallic outer core is what generates Earth's magnetic field through dynamo action. If the Moon has a fluid outer core, why is there no lunar dynamo operating today? The answer appears to be that the lunar outer core is too small and rotating too slowly. The Moon's rotation rate is very slow, once per 27.3 days, to maintain vigorous enough fluid convection to sustain a dynamo. The dynamo that existed in the past likely required a different driving mechanism, perhaps the tidal distortion of the early Moon by the closer early Earth, providing a more effective stirring of the fluid core. Understanding the current state of the lunar core is important because it constrains the thermal history and the past magnetic history of the Moon. A partially molten zone at the base of the mantle suggests that the Moon's interior is not completely solidified, that there is still a boundary between solid and partially liquid material at depth. This has implications for the deep moonquakes, which originate in this depth range, and which may be related to the physical properties of this boundary zone. The InSight lander, NASA's seismometer placed on Mars in 2018, demonstrated the scientific power of a single, highly sensitive seismometer on another planetary body. InSight characterized the internal structure of Mars in detail that would not have been possible from orbital observations alone. A similar instrument on the lunar far side, positioned to complement the Apollo near-side network and provide a global perspective on lunar seismicity, would dramatically improve our understanding of the lunar interior. Such an instrument is part of the scientific rationale for the Farside Seismic Suite, a small seismometer package that has been proposed for delivery to the lunar far side as part of the NASA Commercial Lunar Payload Services program. If delivered and successfully operated, it would provide the first seismic measurements from the lunar far side and would help characterize the interior structure from a different geometric perspective than the Apollo network provided. Let us now talk about the lunar magnetic history in more detail, because the story of how the Moon had a magnetic field and lost it is one of the more complex and interesting detective stories in planetary science. The evidence that the Moon had a dynamo comes primarily from the paleomagnetic signatures in returned Apollo samples. Rocks that cool through their Curie temperature, the temperature below which magnetic minerals lock in the ambient magnetic field, while a field was present, retain that field as a permanent magnetization. The Apollo samples showed that many lunar rocks are magnetized, and their magnetization intensities, analyzed carefully, can constrain the strength of the ancient field. Early analyses suggested that the ancient lunar magnetic field was surprisingly strong, comparable in some cases to Earth's current surface field. This was unexpected because models of lunar dynamo generation had difficulty producing such strong fields. More recent analyses have been more careful to account for alteration effects. Rocks can be remagnetized by shock from subsequent impacts, and have produced a more nuanced picture. The current best understanding is that the Moon had a dynamo that operated from approximately 4.2 billion years ago to approximately 1 billion years ago, spanning most of lunar geological history. The field strength was highest in the early period, when the dynamo was most vigorous, and declined over time as the core cooled and convection weakened. The field appears to have been particularly strong approximately 3.5 billion years ago, a period that coincides with intensive volcanic activity on the near side, which has led to speculation that the volcanic activity may have affected core convection and dynamo generation. Why did the lunar dynamo eventually stop? The most straightforward explanation is that the core cooled to the point where fluid convection was no longer vigorous enough to sustain the dynamo. As the Moon's interior cooled, the outer core solidified progressively from the outside inward, reducing the volume of fluid core available for dynamo action until the dynamo extinguished. This is the same process that eventually awaits Earth's dynamo, though on a much longer timescale given Earth's larger size and higher internal heat budget. But there are complications. Some researchers have proposed that the lunar dynamo was driven not by thermal convection, the standard model for planetary dynamos, but by mechanical stirring. Two mechanisms have been proposed. Precession, the wobbling of the Moon's rotation axis driven by Earth's gravitational torque, can drive fluid flow in the core that might sustain a dynamo. Impact bombardment in the early solar system produced large enough disturbances to stir the lunar core and potentially power intermittent dynamo action. Both of these mechanical driving mechanisms have been explored through numerical modelling with mixed results. They can produce dynamo-like fields in some parameter regimes, but whether they operated in the actual Moon during the appropriate time period is not definitively established. Understanding the lunar dynamo history is not just of interest for Moon science. It bears on questions about the early solar system, about the intensity of the magnetic environment in which the early Earth-Moon system formed and evolved, about the role of magnetic fields in protecting early atmospheres from solar wind erosion, and about the general problem of how rocky planetary bodies generate and sustain magnetic fields. Let us now talk about one of the most recently discovered and most puzzling features of the Moon, the presence of glass beads in the lunar soil that contain water trapped from the solar wind. In 2023, a team of researchers analysing samples returned by the Chinese Chang'e 5 mission, which landed in the Rumke volcanic province on the near side of the Moon in 2020, and returned approximately 1.7 kilograms of samples, reported the discovery of water trapped inside impact glass beads in the lunar regolith. Impact glass beads form when meteorites strike the lunar surface and melt the surrounding regolith. The molten material can form spherical droplets that cool rapidly into glass. These tiny glass beads, typically 0.1 to 5 millimeters in diameter, are common in lunar regolith. The surprising discovery was that these glass beads contain water, measured by secondary ion mass spectrometry, one of the most sensitive analytical techniques available. The water content in the glass is modest, hundreds of parts per million, but the total amount of water potentially stored in the global inventory of impact glass beads across the lunar surface could be substantial. Estimates suggest the lunar surface soil could contain water equivalent to hundreds of millions to billions of tons distributed across the globe, locked in these tiny glass spheres. The proposed mechanism is elegant. As solar wind, which carries hydrogen ions, interacts with the lunar surface, it implants hydrogen into surface minerals. When a meteorite impact melts the surface material, the hydrogen and oxygen in the surrounding minerals combine to form water, which is then trapped in the rapidly cooling glass. The glass protects the water from the photolysis and solar wind sputtering that would quickly destroy water molecules on the open surface. This discovery has implications for understanding both the origin of lunar water and its potential accessibility. If significant water is stored in impact glass beads distributed across the sunlit surface, it is more accessible than water locked in permanently shadowed craters near the poles, and it may be extractable by future resource utilization systems that heat the regolith and collect the released water vapor. The SOFIA detection of surface water and the impact glass bead water discovery together suggest that the Moon is not simply a world where water exists only in polar cold traps, but a world with a global water cycle, molecules of water being created by solar wind interactions, transported across the surface, trapped in glass, released by subsequent impacts, and either lost to space or redistributed to colder regions. The scale and dynamics of this cycle are still being characterized. Let us now talk about the Moon's strange asymmetry, the profound difference between the near side and the far side that remains one of the fundamental unsolved problems in lunar science. If you look at the Moon's near side, the hemisphere that always faces Earth, you see the Maria, the dark, flat volcanic plains that give the familiar face of the Moon its characteristic appearance. These basaltic plains cover approximately 31% of the near-side surface. They formed when the lunar interior was hot enough to produce extensive volcanism between approximately 3 and 4 billion years ago. The far side has almost none of this. Far side mare coverage is less than 2%. The far side is dominated by ancient highland terrain, heavily cratered, uniformly pale, geologically ancient, almost entirely lacking the volcanic flooding that resurfaced large portions of the near side. The two hemispheres are fundamentally different worlds. This difference is called the lunar dichotomy, and it is one of the fundamental mysteries of lunar science. The leading hypothesis involves crustal thickness. The crust on the far side is significantly thicker than on the near side. The near side crust averages approximately 30 to 40 kilometers, while the far side averages approximately 50 to 60 kilometers, and in some regions exceeds 80 kilometers. A thicker crust is harder for magma from the interior to penetrate. So even when the lunar interior was hot enough to produce magma, the far side crust was thick enough to prevent most of it from reaching the surface. But why is the far side crust thicker? Multiple hypotheses exist, and none is fully satisfactory on its own. One involves the asymmetric solidification of the early lunar magma ocean, the global layer of molten rock that covered the Moon shortly after formation. If the near side cooled more slowly than the far side, perhaps because it was facing the hot early Earth, whose thermal radiation slowed near side cooling, the crystallization pattern would have been different and could have produced the observed asymmetry. Another involves a giant impact on the far side early in lunar history that produced the South Pole-Aitken basin, at 2,500 kilometers diameter, the largest confirmed impact crater in the solar system, and whose effects on the crustal structure of the early Moon are still being modelled. A third involves the concentration of heat-producing radioactive elements on the near side, the Carib terrain. If heat-producing elements are preferentially concentrated near side, the near side mantle has been hotter than the far side mantle throughout lunar history, sustaining more extensive volcanism over a longer period. The Grail mission provided the most precise map of the lunar gravitational field ever obtained, and its data placed new constraints on the crustal thickness asymmetry. Grail confirmed the thickness difference and revealed additional structure. The crust is not uniformly thick even within each hemisphere, but has local variations reflecting the history of large impacts that excavated and redistributed crustal material. Understanding the lunar dichotomy is not simply a question about the Moon in isolation. It is connected to the broader question of how the Moon formed and how the Earth-Moon system evolved in its first billion years. The asymmetry of the Moon is a record of initial conditions and early processes that are also relevant to the early Earth. And since we have access to lunar samples in a way we do not have access to the deep geological record of the early Earth, which has been erased by plate tectonics and erosion, the Moon is our best window into conditions in the inner solar system 4 billion years ago. Let us now talk about what recent and upcoming missions are revealing and will reveal about the strange Moon we have been describing. The current era of lunar exploration is more active than any period since Apollo. China's Chang'e program has successfully returned samples twice, Chang'e 5 in 2020 from the near-side Rumka volcanic province, and Chang'e 6 in 2024 from the Apollo crater within the South Pole-Aitken basin on the far side, the first far-side sample return in history. The Chang'e 6 samples are now being analysed, and initial results are already providing new information about far-side volcanic history and the composition of the South Pole-Aitken basin floor. India's Chandrayaan-3 successfully landed in the lunar South Polar region in August 2023, the first spacecraft to land near the lunar South Pole. The Pragyan rover conducted surface observations and measurements before the lunar night ended the mission. The data from Chandrayaan-3 is being analysed and contributes to the growing characterization of the South Polar environment. Japan's SLIM lander, smart lander for investigating Moon, successfully landed in January 2024, becoming the first Japanese spacecraft to soft land on the Moon, though it landed in an unusual orientation. The mission demonstrated precision landing technology that will be important for future missions targeting specific scientific sites. NASA's Artemis program, after the crewed Artemis II flyby of the Moon in 2024, is building toward the Artemis III crewed landing near the South Pole, planned for the mid to late 2020s. The South Polar landing will target the investigation of permanently shadowed regions and their water ice content, while also conducting broader geological fieldwork in an area that has never been visited by any previous mission. The scientific questions these missions are addressing, the water distribution, the heat flow, the seismic activity, the volcanic history, the magnetic anomalies, the plasma environment, are all pieces of the larger puzzle of understanding what the Moon is doing and why. Each mission answers some questions and invariably opens new ones. The Moon that we are exploring today is not the simple dead world that many people assumed after Apollo. It is a world with active geological processes, slow, subtle, but real. It is a world with water in unexpected places. It is a world with magnetic anomalies whose origin connects to the history of the early solar system. It is a world still releasing heat from its interior. It is a world still shaking. The strangeness is not a sign of something wrong. It is a sign of how much we did not know and how much we are still learning. The Moon is the closest other world to Earth, the one we have studied most and visited most, and it is still surprising us, still revealing aspects of its nature that our models did not predict, still posing questions that our best theories have not yet answered. This is what science at its best looks like, not the triumphant proclamation of complete understanding, but the honest confrontation with the gap between what we expected and what we find. The Moon is strange, our models are incomplete, the investigation continues. And the investigation will accelerate over the coming decades as more spacecraft land, more samples return, more seismometers listen, and eventually as human beings return to the surface not just to plant flags, but to do the kind of patient, systematic field science that can begin to resolve the mysteries that 4 decades of robotic exploration have accumulated. The Moon is waiting. It has been there for 4.5 billion years. It has been watching Earth evolve from a molten hellscape to a world of oceans and life and civilization. It has been slowly cooling, slowly contracting, occasionally shaking, intermittently glowing, accumulating water in its shadows and on its sunlit plains, maintaining its strange swirls and its magnetic memories of an ancient dynamo. And we are just beginning to understand what it is. Let us talk about something that connects all these individual lunar mysteries. The question of whether they are truly independent phenomena or whether they reflect a single underlying reality about the Moon that our models have systematically underestimated. The standard model of the Moon that emerged from Apollo was elegant in its simplicity. The Moon formed in a giant impact. It differentiated rapidly with a magma ocean covering its surface. It cooled. The KREEP-rich material concentrated on the near side. Volcanism proceeded vigorously for the first billion years and then declined as the interior cooled. By approximately 3 billion years ago, the Moon was geologically essentially dead, a preserved fossil of the early solar system, its surface telling the story of the first billion years of bombardment and volcanism, but no longer actively changing. This model is not wrong in its broad outlines. The giant impact formation is supported by strong evidence. The specific isotopic composition of lunar samples compared to Earth samples, the angular momentum of the Earth-Moon system, the depletion of volatile elements in the Moon relative to Earth. The magma-ocean differentiation is supported by the anorthositic composition of the lunar highlands. The early volcanic history is confirmed by the ages of the Maria samples. What the model got wrong, or at least significantly underestimated, was the degree to which the Moon has remained active in its later history. The heat flow measurements higher than predicted, the young scarps still forming, the seismicity still occurring, the water present in unexpected places, the magnetic anomalies requiring a dynamo that operated longer than expected, the possible young volcanism. Each individual anomaly might be explained away as a local phenomenon or a measurement artifact. But the accumulation of anomalies, the pattern of the Moon being more active than predicted across multiple independent lines of evidence, suggests that our fundamental understanding of lunar thermal evolution may need revision. One specific area where revision may be needed is the role of tidal heating. Earth's tidal forces act on the Moon, the same forces that are causing the Moon to recede from Earth and slowing Earth's rotation. These tidal forces deform the Moon slightly as it moves through its slightly elliptical orbit. The Moon is physically distorted by Earth's gravity, stretching and relaxing as its distance from Earth changes. This physical distortion generates heat through internal friction, tidal heating. For small bodies close to their host planet, tidal heating can be enormous. Io, the innermost large moon of Jupiter, is the most volcanically active body in the solar system, specifically because Jupiter's powerful tidal forces generate immense amounts of heat in its interior. For the Moon, the effect is much smaller. Earth is less massive than Jupiter, and the Moon is farther from Earth in relative terms than Io is from Jupiter. But it may not be entirely negligible. If tidal heating has contributed measurably to maintaining the Moon's interior at higher temperatures than a purely thermally cooling body would achieve, it could explain why the Moon appears warmer and more active than simple cooling models predict. The contribution of tidal heating to lunar thermal history has been calculated in various models, with differing results depending on assumptions about the Moon's interior rheology, how deformable the interior is in response to tidal forces. This is a quantitative question that requires better constraints on the Moon's interior properties, specifically on the viscosity and partial melt fraction of the deep mantle, to resolve definitively. The seismic data from a next-generation lunar seismic network would provide these constraints. This is one of the highest priority science goals for future lunar missions, as articulated in NASA's Planetary Science Decadal Survey. Let us now talk about the South Pole-Aitken Basin specifically, because this feature is central to what makes the Moon scientifically extraordinary, and several of the mysteries we have been discussing connect directly to it. The South Pole-Aitken Basin is the largest confirmed impact crater in the solar system. It is approximately 2,500 kilometers in diameter and approximately 8 kilometers deep, extending from the lunar South Pole to a point near the equator on the far side. The impact that created it, approximately 4.2 billion years ago, was one of the most energetic events in the history of the Moon. The impacting object may have been 200 kilometers in diameter or larger, a body large enough that its impact fundamentally restructured the lunar crust over a substantial fraction of the Moon's surface. The floor of the basin is at some of the lowest elevations on the Moon. The rim stands at some of the highest. The total relief from basin floor to rim crest in some places exceeds 12 kilometers, greater than the height of Mount Everest above sea level. If you stood at the center of the South Pole-Aitken Basin and looked toward the rim, you would be looking up at walls kilometers high over a distance of more than 1,000 kilometers. A horizon so far away it would curve noticeably below the level of the crater floor due to the Moon's curvature. The scientific significance of the South Pole-Aitken Basin is extraordinary for multiple reasons. First, an impact this large and this deep excavated material from deep within the lunar interior, material that formed at depths of perhaps 40 to 60 kilometers or more, material that has never been on the surface since the Moon solidified. This excavated material should include the lower crust and possibly mantle material, rock types that are not accessible anywhere else on the lunar surface without drilling to extreme depths. Studying the composition of the South Pole-Aitken Basin floor is studying the Moon's interior indirectly. The Chinese Chang'e 4 mission, landing in the von Karman crater within the South Pole-Aitken Basin, specifically chose this site to access this scientifically valuable material. The U-22 rover's spectrometers detected olivine and pyroxene, minerals from the deeper lunar crust or mantle in the crater floor material, consistent with the hypothesis that the South Pole-Aitken impact excavated deep-seated material. Chang'e 6 returned samples from the Apollo crater, also within the basin, and initial analysis of these samples is providing new constraints on the composition of the basin floor and on the age of farside volcanism. Second, the South Pole-Aitken Basin is connected to the permanently shadowed regions that contain water ice. The basin extends into the South Polar region, where the lowest permanently shadowed craters are located. Some of the most ice-rich permanently shadowed regions are within or adjacent to the basin. This means that future missions targeting both the scientific questions of the basin floor composition and the practical questions of water ice availability may converge on the same geographic area. Third, the basin's formation may have been the triggering event for several other lunar mysteries. The antipodal effects of the impact, shock waves focusing on the near side opposite the basin, may have contributed to the magnetic anomalies on the near side. The enormous excavation may have redistributed creep-bearing material from the deep lunar interior across the near side. The disruption of the lunar crust over such a large area may have influenced the pattern of subsequent volcanism. In this sense, the South Pole-Aitken Basin is not just a scientific target in itself. It is potentially the key to understanding multiple aspects of lunar history simultaneously. The origin of the lunar dichotomy, the distribution of creep material, the near-side magnetic anomalies, and the pattern of near-side volcanism may all trace back to a single cataclysmic event approximately 4.2 billion years ago. Let us now talk about something that connects the lunar mysteries to the broader question of what rocky planets and moons look like from the inside, and why the Moon is a uniquely valuable laboratory for understanding planetary evolution. Earth's interior is largely inaccessible. The deepest borehole ever drilled, the Kola super-deep borehole in Russia, reached 12.2 kilometers, a depth that barely scratches the surface of the roughly 6,371 kilometer radius of the Earth. Everything we know about Earth's interior below the crust comes from seismic waves, from monitoring how earthquake waves travel through the Earth and inferring the properties of the layers they pass through. Mars has been studied seismically by the InSight mission, and we now have a detailed picture of its interior structure. Mercury has been studied by Messenger and Bepi Colombo, but without seismic data, its interior remains less precisely characterized. Venus, similar in size to Earth, has essentially no interior characterization because no seismometer has survived on its surface for more than a few hours. The Moon stands apart because we have both seismic data from the Apollo network and physical samples from Apollo and more recently from Chang'e 5 and Chang'e 6. The combination of seismic constraints on interior structure and geochemical constraints from samples on the composition of materials at different depths makes the Moon uniquely well characterized among the rocky bodies of the solar system. And yet, as we have been discussing, our understanding remains incomplete. The Apollo seismic network was limited in coverage and sensitivity. The samples are from a small geographic area of the near side. The interior structure, inferred from combining all available constraints, still has substantial uncertainties, particularly regarding the core and the deep mantle. Improving this understanding requires two things that future lunar missions are specifically designed to provide. First, a new seismic network with better coverage and sensitivity than Apollo, ideally including a far-side station to complete the global picture. Second, samples from geologically diverse locations, including the far side, the South Pole-Aitken basin floor, and the Kiri-Pur highland crust, away from the Oceanus Procellarum region. Both of these goals are explicitly part of the NASA Lunar Discovery and Exploration Program and the science objectives of the Artemis program. The scientific community has articulated them clearly in the Planetary Science Decadal Survey and in the Lunar Exploration Roadmap. The question is not what science to do, it is how quickly the technical and financial resources can be assembled to do it. Let us now talk about what the Moon's strangeness means specifically for the question of habitability, not for life on the Moon itself, which is almost certainly absent, but for what the Moon tells us about what makes rocky worlds habitable in general. The Moon is not habitable in any conventional sense. Its surface is exposed to radiation, extreme temperature swings, micrometeorite bombardment, and vacuum, conditions lethal to all known life. Any life that might exist there would have to be buried deep in the regolith or in subsurface cavities sheltered from the surface environment. There is no evidence for such life, and strong reasons to think it does not exist. But the Moon's geological history is directly relevant to questions about habitability in a different sense. The early Moon was hot. Its surface was covered in a magma ocean for tens to hundreds of millions of years after formation. It had volcanic activity, generating gases that produced a transient lunar atmosphere, thin and short-lived, but real. It had water, delivered by cometary and asteroidal impacts during the period of heavy bombardment. It had a magnetic field, providing some protection from solar wind. For a brief window in the very early history of the Moon, perhaps 3.5 to 4 billion years ago, conditions at the surface may have been more hospitable to chemistry, if not to life as we know it. The volcanic outgassing, the impactor-delivered volatiles, and the presence of liquid water on timescales too short for sustained habitability, but long enough for complex chemistry. All of these conditions existed on the Moon at the same time they existed on the early Earth. This suggests that the chemistry that preceded life on Earth, the prebiotic chemistry that produced the molecules from which life eventually assembled itself, occurred in a solar system environment where the Moon was geologically active and chemically complex, rather than the dead, dry world it is today. Understanding what the early Moon was like, therefore, contributes to understanding the environment in which life originated on Earth. More broadly, the Moon's thermal history, the way it has cooled, the rate at which its interior has retained or lost heat, the influence of tidal heating and radioactive decay on its temperature profile, is a case study in how rocky bodies of a particular size evolve. This is relevant for understanding the habitability of rocky worlds in general. Planets and moons of different sizes have different thermal histories. Larger bodies cool more slowly, smaller bodies cool faster. The Moon's specific thermal history, between the very small and rapidly cooled rocky bodies like asteroids and the very large and still thermally active bodies like Earth, fills in part of the picture. Let us now talk about the role of the Moon in stabilizing Earth's climate, because this is one of the most practically significant ways in which the Moon's specific properties affect the habitability of Earth. Earth's rotation axis is tilted at approximately 23.5 degrees from the perpendicular to its orbital plane. This tilt, called the obliquity, is what produces the seasons. When the northern hemisphere is tilted toward the Sun, it receives more sunlight and experiences summer. When it is tilted away, it receives less and experiences winter. The obliquity of Earth is not fixed. It oscillates over time due to gravitational influences from the other planets. Without any stabilizing influence, the obliquity of a planet can vary widely and chaotically. Calculations show that without the Moon, Earth's obliquity could potentially vary between nearly 0 degrees and as much as 85 degrees over timescales of millions of years. The Moon stabilizes Earth's obliquity. The gravitational torque exerted by the Moon on Earth's equatorial bulge, the slight equatorial excess mass that results from Earth's rotation, acts as a gyroscopic stabilizer. It prevents the slow, chaotic drift of the rotation axis that would otherwise occur under the combined gravitational influence of the other planets. With a stable obliquity, Earth has stable seasons. The same hemisphere receives more sunlight in summer and less in winter, year after year, with only gradual changes over timescales of tens of thousands of years, the Milankovitch cycles, rather than rapid, chaotic swings over millions of years. This stability appears to be important for the long-term persistence of a biosphere because life, and particularly complex life, requires a relatively stable climate over geological timescales to evolve and diversify. Mars, which has no large moon, has experienced large variations in its obliquity over its history. Mars's obliquity has ranged from near zero to as high as 45 degrees or more over the past few billion years, according to numerical simulations. These large obliquity variations have dramatically altered the Martian climate, shifting ice between polar caps and tropical regions, changing atmospheric pressure as carbon dioxide ice redistributizes, altering the distribution of liquid water when it existed. Whether this climate instability contributed to Mars's apparent habitability decline is debated, but the comparison with Earth is suggestive. The Moon, therefore, may be not just an interesting object for scientific study, but an important contributor to Earth's habitability, a stabilizing influence whose absence would have produced a significantly more volatile climate over Earth's history. Understanding the Moon's specific role in the Earth system is part of understanding why Earth is as habitable as it is. Let us now talk about what the next decade of lunar science is likely to reveal, given the missions currently in development and the scientific questions they are designed to address. The Viper rover, NASA's Volatiles Investigating Polar Exploration rover, is planned to explore the lunar South Polar region in detail, searching for water ice. Viper will drill into the regolith at multiple locations, measuring ice concentration as a function of depth and location. This will be the most comprehensive characterization of lunar water ice ever conducted, and will directly address the distribution and accessibility of ice in permanently shadowed regions. The Lunar Trailblazer mission, a small NASA science spacecraft, will map the distribution of water and hydroxyl across the lunar surface using infrared spectroscopy from orbit. This global map will extend the Sophia observations to the entire Moon and will characterize the spatial and temporal variability of surface water, tracking how the distribution changes with lunar day and night and with position on the surface. The Lunar Flashlight mission, a small NASA CubeSat, was designed to search for ice in permanently shadowed craters using near-infrared lasers. Unfortunately, the mission encountered propulsion issues that prevented it from reaching lunar orbit. But the scientific approach, active illumination of permanently shadowed regions to detect ice, will likely be pursued in future missions. The Commercial Lunar Payload Services program is delivering small scientific payloads to diverse locations on the lunar surface through commercial landers. Multiple CLPS deliveries are planned over the coming years, targeting different landing sites and carrying a variety of scientific instruments. These missions will collectively characterize the lunar environment at many locations for the first time, expanding our picture beyond the 6 Apollo landing sites, which were all near the equator on the near side. The planned Farside Seismic Suite will place a seismometer on the lunar far side for the first time, complementing the Apollo near-side network and providing the first seismic measurements from the opposite hemisphere. Combined with the Apollo data and any future seismometers placed at additional locations, this will enable a 3-dimensional model of the lunar interior at significantly better resolution than currently possible. China's Chang'e 7 and Chang'e 8 missions, planned for the late 2020s, will continue Chinese lunar exploration with increasingly capable systems. Chang'e 7 will explore the South Polar region with an orbiter, lander, rover, and a small flying detector capable of entering permanently shadowed craters to look for ice. Chang'e 8 will test technologies for in situ resource utilization, using lunar materials to produce oxygen and other useful products. The cumulative effect of all these missions, NASA, commercial, international, will be a picture of the Moon significantly more complete than we have today. The water distribution will be mapped. The seismic network will be extended. Additional landing sites will be characterized. Samples will return from diverse locations. The specific anomalies and mysteries we have been discussing, the heat flow question, the young volcanism question, the magnetic anomaly origin question, will receive new data that will either resolve them or sharpen them into more focused questions. And then there will be the humans. When Artemis 3 lands near the South Polar region, it will put geologically trained human beings in an environment that no robot has fully characterized and that no human has ever visited. The specific discoveries that human field scientists make in the South Polar environment, adapting their investigation in real time to what they find, following unexpected observations wherever they lead, exercising the kind of flexible scientific judgment that is the essence of good field geology, cannot be fully predicted. This is what makes human lunar exploration scientifically irreplaceable. Not that humans can do everything robots cannot, but that in complex environments with multiple interacting geological and physical phenomena, which is exactly what the lunar South Pole is, human presence and human judgment accelerate the rate of discovery in ways that are difficult to quantify but consistently demonstrated by the history of scientific fieldwork. The Apollo missions confirmed this dramatically, In 3 years of Apollo surface operations, a total of approximately 80 human hours on the lunar surface, the astronauts collected 381 kilograms of samples from 6 locations, identified geological features that orbital photography had not revealed, and made observations that shaped our understanding of the Moon for half a century. The specific decision to collect a particular rock, to notice that one area looked different from another, to dig a trench in a particular location. These human judgments, made in real time based on direct observation, produced data that would have been very different if collected by a pre-programmed robot following a fixed plan. The Moon is waiting for this kind of attention again, with 50 additional years of remote sensing data to focus the investigation, with better analytical tools to make sense of what is found, with specific scientific questions: the water distribution, the heat flow, the seismicity, the recent volcanic activity, that the Apollo era could not fully address. The Moon is strange. The strangeness is an invitation. It is the universe telling us through data that our understanding is incomplete, that what we thought was a solved problem, what is the Moon, what is it doing, why is it the way it is not solved. Every anomaly in the heat flow measurements is a message from the lunar interior saying, "I am not what you thought." Every young scarp still forming is the crust moving in slow motion saying, "I am not dead." Every water molecule on the sunlit surface where it should not be is the surface chemistry saying, "I am more complex than your models." Every unexplained transient glow is the interface between the lunar surface and space, saying, "I am not simply empty." These messages have been accumulating for decades. We are finally developing the instruments and the missions and the presence to read them properly. Let us talk about something that rarely appears in discussions of lunar science, but that is central to understanding why the Moon behaves the way it does: the specific role of the early giant impact in determining everything that came after. The giant impact hypothesis, the idea that the Moon formed when a Mars-sized body called Theia collided with the early Earth approximately 4.5 billion years ago, is the most widely accepted model for lunar origin. It explains several key features: the specific angular momentum of the Earth-Moon system, the Moon's relatively low density compared to Earth, suggesting it is depleted in iron, the similarity between Earth and lunar isotopic compositions, suggesting they formed from the same material, and the Moon's depletion in volatile elements, suggesting formation at high temperatures. But the giant impact hypothesis is not without complications, and some of these complications connect directly to the current strangeness of the Moon. The specific geometry of the impact, the angle, the velocity, the relative masses of the impactor and target, determines what fraction of the final Moon came from the impactor versus from the early Earth's mantle. The impactor Theia presumably formed in a different part of the early solar system and would have had a different isotopic composition from Earth. But the Moon's isotopic composition is remarkably similar to Earth's in multiple isotopic systems: oxygen, tungsten, titanium. Too similar for most standard giant impact models, which predict the Moon should be dominated by impactor material. This led to various modified impact scenarios. A higher velocity impact might have mixed the material more thoroughly, producing a more Earth-like composition. A more head-on impact by a smaller impactor might have preferentially ejected Earth mantle material. A series of smaller impacts, rather than one giant one, might have built the Moon incrementally. Each of these scenarios has different predictions for the detailed properties of the Moon, and none is entirely satisfactory. The most recent development in this debate involves the synestia model. A synestia is a rapidly rotating donut-shaped structure of vaporized rock that can form when a large impact delivers enough angular momentum and energy to completely vaporize and mix a significant fraction of the colliding bodies. In this model, the Moon condenses from the synestia, from vaporized mixed Earth-Theia material, which explains the isotopic similarity between Earth and Moon, because the synestia is thoroughly mixed before condensing. The Moon forms from the inner part of the synestia, which is compositionally most similar to Earth's mantle. The synestia model makes specific predictions about the Moon's composition and physical properties that are testable against samples. Some features of the model are supported by the compositional data, others are still being evaluated. The formation story of the Moon is not closed. It is an active area of theoretical and observational research. What is relevant to the current strangeness of the Moon is that the specific impact scenario determined the initial conditions, the initial temperature profile, the initial composition distribution, the initial rotation rate, from which all subsequent lunar evolution proceeded. If the Moon formed through a synestia rather than direct impact condensation, its initial thermal state and compositional distribution would have been different from standard giant impact models, potentially with implications for how it has evolved since. Let us now talk about the relationship between the Moon's magnetic history and the history of life on Earth, because this connection, rarely discussed in popular science, is one of the most intriguing implications of the lunar dynamo research. Earth has a strong global magnetic field, the magnetosphere, that deflects the solar wind and most charged particle radiation. This magnetosphere is generally considered important for maintaining Earth's atmosphere against solar wind stripping, the process by which solar wind ions can interact with atmospheric particles and gradually remove them to space. Mars, which apparently lost its dynamo approximately 4 billion years ago, subsequently lost most of its atmosphere and its surface water, though the extent to which the dynamo loss caused the atmospheric loss versus other factors remains debated. The early Moon, when it had an active dynamo, generated its own magnetosphere. While the lunar magnetosphere was much weaker than Earth's current magnetosphere, it provided some degree of shielding. During the period when both Earth and the Moon had active dynamos, approximately 4 to 2 billion years ago, the magnetic environment of the inner Earth-Moon system was different from today. One specific implication involves cosmic ray shielding. Galactic cosmic rays, high-energy charged particles from outside the solar system, are partially deflected by planetary magnetic fields. Earth's magnetosphere deflects a significant fraction of cosmic rays reaching its vicinity. A stronger early magnetic field would have provided more cosmic ray shielding for the early Earth's surface. The connection to life is through the mutational effect of cosmic rays. High-energy particles ionize biological molecules and can cause DNA damage. Over geological timescales, changes in the cosmic ray flux reaching Earth's surface would affect mutation rates and the pace of evolutionary change. Some researchers have speculated that periods of reduced magnetic shielding, associated with geomagnetic reversals when Earth's field weakens and sometimes reverses polarity, may correlate with periods of elevated extinction or evolutionary change in the fossil record. The Moon's magnetic history adds another layer to this story. As long as the Moon had an active dynamo, it contributed to the local magnetic environment of the Earth-Moon system. After the lunar dynamo extinguished approximately 1 to 2 billion years ago, the Moon was no longer magnetically active. Whether this transition produced any measurable effect on Earth's cosmic ray environment or on the magnetospheric environment more broadly is a question that connects lunar magnetic history to the history of life on Earth. This connection is speculative at the current level of scientific understanding. The specific quantitative effects of the lunar dynamo on Earth's cosmic ray environment are not well calculated. But the connection exists in principle, and the data on lunar magnetic history from return samples is progressively improving our ability to characterize when the lunar dynamo operated and at what strength. Future samples from diverse lunar locations with diverse ages will refine this picture further. Let us now talk about something that connects all the physical phenomena we have been discussing to the human experience of the Moon, about how the specific physical strangeness of the Moon that we have been describing has manifested in human observations over centuries. Long before anyone understood what moonquakes were, or what magnetic anomalies were, or what water ice in permanently shadowed craters represented, human beings were observing the Moon and noticing that it behaved strangely in specific ways. The transient phenomena, the flashes and glows and obscurations that we now understand as a complex interplay of impacts, degassing and electrostatic effects, were being recorded by careful observers for centuries. The crater Aristarchus, one of the brightest features on the lunar surface, located in the Aristarchus Plateau, which is one of the most geologically diverse and scientifically interesting regions on the Moon, has been the focus of transient phenomenon reports for more than 200 years. Observers as careful and credible as William Herschel, the discoverer of Uranus and one of the greatest observational astronomers in history, reported seeing glowing spots in the Aristarchus region that he described as 3 volcanoes on the Moon in 1787. Herschel was almost certainly not seeing active volcanism in the modern sense, but he was seeing something real, some transient brightening or emission from a region that we now know is geologically unusual, sitting on the KREEP-rich terrain, associated with magnetic anomalies, in a region where subsequent orbital spacecraft have detected elevated concentrations of radon, indicating ongoing gas emission. The history of lunar transient phenomenon observations is a history of careful observers noticing that the Moon is not entirely static, noticing, in the language of their time and with the instruments of their time, that something was happening on the lunar surface that simple geological death should not produce. The observations accumulated over centuries without a coherent explanation because the underlying physics of electrostatic dust lofting, of impact flash generation, of degassing from a slowly cooling interior was not understood. Now we have the physics. We can look at the historical observations with modern understanding and recognize what was likely being seen. Impact flashes during meteor showers, electrostatic disturbances at the terminator during solar events, possible radon-associated glows over geologically active regions. The observations were real. The interpretation was wrong. The physical phenomena being reported were genuine, even when the explanations offered, active volcanism, inhabiting aliens, optical illusions, were incorrect. This is a pattern that repeats throughout the history of science. Careful observers reporting anomalous phenomena that their theoretical framework cannot explain. The anomalies accumulate. A new framework eventually emerges that explains them. The observations were always pointing toward the correct physical reality. They just needed the theoretical understanding to make sense of. The lunar anomalies we have been discussing, the higher than expected heat flow, the young scarps, the surface water, the swirls, the transient phenomena, are in some ways the modern version of this pattern. We are the careful observers. We have better instruments than Herschel. We have better theoretical frameworks. But we are still in the position of accumulating anomalies faster than we can fully explain them. The Moon is still telling us something that our current understanding does not fully capture. Let us now talk about what the Moon looks like from the inside of these ongoing scientific debates, about the specific texture of how scientists are working through these questions. Lunar science has experienced something of a renaissance in the past 15 years. After a period of relative quiet following the end of Apollo, when the community was primarily analysing existing samples and orbital data, the new wave of orbital missions, Lunar Reconnaissance Orbiter, GRAIL, LADEE, Chandrayaan-1 and 2, Kaguya, Chang'e series, has produced a flood of new data of types and quality not available before. This new data has reopened questions that seemed settled and raised new ones that nobody thought to ask before. The water question is a good example. For decades after Apollo, the consensus was that the Moon was dry. The Apollo samples were dry. End of question. It took a series of gradually improving orbital measurements and eventually the severe detection of water molecules on the sunlit surface to overturn this consensus. At each stage, there was resistance from established views. At each stage, the new data was examined skeptically and alternative explanations were sought. Eventually, the accumulation of evidence became too strong to dispute. This is how science works in practice, not through sudden dramatic revelations, but through the gradual accumulation of evidence that eventually reaches the threshold where the community accepts a new interpretation. The process is messier and more contested than the textbook version suggests. Careers are invested in particular interpretations. Data is ambiguous and requires interpretation. Alternative explanations always exist and must be ruled out carefully. The young volcanism question is currently at an earlier stage of this process. The IMP features have been identified. The crater counting suggests they are young, but the alternative interpretation, that they are simply small features with poor crater statistics, has not been definitively ruled out. The community is divided. Samples from potential IMP sites would provide the definitive evidence, but obtaining such samples requires landing at a specific, scientifically targeted location, which has not been done outside the Apollo program. The heat flow question similarly awaits more data. 2 measurements from adjacent sites in an unusual part of the Moon are insufficient to characterize the global heat flow. More measurements from more locations, particularly the far side, will either confirm that the anomalously high near-side values are genuinely representative of the Moon's thermal state, or reveal that they are KREEP-specific local phenomena. The scientific community working on these questions includes hundreds of researchers across dozens of countries, with overlapping and sometimes competing interpretations. The debates are conducted in scientific journals, at conferences like the Lunar and Planetary Science Conference, which meets annually in Houston, and increasingly in preprint archives, where results are shared rapidly before formal publication. The community is small enough to know each other personally, but large enough to have genuine diversity of perspective. What they share is access to increasingly powerful tools, high-resolution orbital imagery from Lunar Reconnaissance Orbiter that can resolve features less than a meter across, compositional mapping from infrared and gamma-ray spectrometers, gravity measurements of extraordinary precision from GRAIL, seismic data being reanalyzed with modern algorithms. They are bringing 21st century tools to bear on data collected across 5 decades of lunar exploration, and finding that the data is richer than we knew. Let us now talk about what the Moon's ongoing activity means for future human inhabitants, for the people who will eventually live and work on the lunar surface for extended periods. The young scarps and ongoing moonquakes mean that the Moon is not seismically quiet. The magnitude 5.5 moonquakes that occur occasionally are significant events. On Earth, a magnitude 5.5 earthquake causes moderate damage to poorly constructed buildings. On the Moon, with no atmosphere to attenuate seismic waves, the shaking would be sustained for much longer than a comparable terrestrial earthquake, because the Moon's interior transmits seismic energy with lower damping than Earth's wetter, more plastic interior. Apollo seismometers recorded moonquakes that lasted for up to an hour, the seismic energy ringing in the relatively dry, fractured lunar crust far longer than a comparable earthquake would last. A magnitude 5.5 moonquake that shakes for 30 minutes is a very different engineering challenge from an earthquake of the same magnitude that is over in 30 seconds. Lunar habitats, equipment foundations, and surface structures will need to be designed with this sustained seismic environment in mind. The water distribution question directly affects habitat site selection and resource planning. If water ice is accessible in modest concentrations over wide areas near the South Pole, as the glass bead discovery suggests may be possible even beyond permanently shadowed craters, the strategic value of specific permanently shadowed crater sites is changed. If water is primarily concentrated in the very coldest permanently shadowed regions, the engineering challenge of extracting it is more severe. Operating equipment at temperatures of -200 degrees Celsius and below requires specialized materials and designs that function at cryogenic temperatures. The lunar plasma environment, the electrostatic charging and potential dust lofting, creates a hazard for surface operations that is still not fully characterized. Charged dust that adheres to surfaces can degrade optical systems, clog mechanical joints, and coat solar panels, reducing their efficiency. Apollo astronauts found that lunar dust was pervasive and problematic, despite spending only a few hours on the surface. For habitats and equipment spending months or years on the surface, dust management becomes a critical engineering challenge. Understanding the electrostatic dynamics that drive dust behavior is essential for developing effective mitigation strategies. The radiation environment, including both solar energetic particles and galactic cosmic rays, requires habitat shielding. The most practical approach for surface habitats is to use the regolith itself as shielding. Piling several meters of regolith over the habitat structure attenuates the radiation to acceptable levels. But the regolith's specific shielding effectiveness depends on its composition and density, which vary by location. The detailed radiation environment monitoring being conducted by current and future missions will provide the input data for shielding design. The transient phenomena, the impact flashes and surface events, represent a background hazard for surface operations. The rate of impacts large enough to be hazardous to surface equipment or personnel is low, but not zero. The Neliota program is providing the best current data on the rate of visible impact events. For near-term, Apollo-style brief surface stays, the impact hazard is manageable. For permanent habitats operating over years and decades, the cumulative probability of a damaging impact in the vicinity of the habitat requires careful assessment. Let us now talk about the Moon's relationship to the broader context of solar system exploration, about what the mysteries of the Moon tell us about our understanding of rocky worlds in general, and what studying the Moon contributes to our ability to understand other worlds. Every rocky world in the solar system went through an early phase of intense bombardment, differentiation, and internal heating. The Moon preserves the record of this early phase more completely than Earth, because Earth's plate tectonics and erosion have erased most of its early geological record, while the Moon's surface has changed relatively slowly for billions of years. The Moon is therefore a time capsule, a preserved sample of conditions in the early inner solar system. The specific anomalies we have been discussing, the anomalous heat flow, the young tectonics, the unexpected water, the magnetic history, are all reflections of the early solar system conditions that are erased on Earth. Resolving these anomalies contributes to understanding not just the Moon, but the broader conditions in which all the rocky planets formed and evolved. The relationship between the Moon's size and its thermal evolution is a case study for understanding why different-sized rocky bodies behave differently. The Moon is small enough to have cooled substantially, but not so small that it is completely cold. It is in an intermediate regime that is actually underrepresented in our collection of well-studied rocky bodies. We have Earth, which is large and still very active. We have Mars, which is intermediate and significantly cooled. We have the asteroids, which are small and essentially thermally dead. The Moon sits between Mars and the asteroids in size, and its thermal behavior occupies the corresponding intermediate position. Understanding where the Moon sits on the spectrum from thermally active to thermally dead is important for understanding planetary habitability more broadly. Small rocky planets around other stars, of which there are many in the galaxy, will have thermal histories more like the Moon's than like Earth's. Understanding the Moon's thermal evolution is therefore a contribution to understanding the habitability of small rocky worlds throughout the galaxy. The Moon's water story, the discovery that water is more widely distributed than expected, present even on sunlit surfaces, stored in impact glass, cycling globally, is a contribution to our understanding of the volatile histories of rocky worlds in general. If water can persist on the Moon's sunlit surface through the glass bead mechanism, it may similarly persist on other airless rocky bodies, asteroids, other moons, the surface of Mercury. The Moon serves as a laboratory for studying surface volatile chemistry under the extreme conditions of solar irradiation and cosmic ray bombardment. Every answer the Moon provides about itself is therefore not only an answer about the Moon, it is a data point for understanding the broader physics and chemistry of rocky worlds. The Moon is the most accessible of all the rocky worlds we might study. It is only a few days' travel away. It has been visited by spacecraft for 6 decades. It has been sampled directly. Its strangeness is our best opportunity to develop and test models that we will then apply to worlds we can only observe from afar. Let us now talk about the specific measurement that would most transform our understanding of the Moon, the measurement that, if we could make it today, would resolve the most outstanding questions. The answer is almost certainly a comprehensive seismic network. The Apollo seismic data, 4 stations on the near side of the Moon operating for 8 years, gave us enormous scientific return for its investment. But it was limited in coverage, in sensitivity, and in duration. A modern network, 3 or more broadband seismometers deployed at diverse locations, including at least one on the far side, operating for a decade or more, would provide a complete picture of the lunar interior that current data cannot achieve. With such a network, we could determine the size and physical state of the lunar core precisely, settling the question of whether the outer core is still fluid and whether convection in it is still occurring. We could map the thickness of the partially molten zone at the base of the mantle precisely, providing the key thermal parameter for understanding the Moon's current thermal state. We could locate the sources of the shallow moonquakes precisely, determining whether they are associated with specific geological features and whether they represent a particular type of tectonic activity. We could determine the velocity structure of the crust and mantle in 3 dimensions, providing the compositional and thermal constraints that current single-site analyses cannot provide. This comprehensive seismic network would answer most of the outstanding interior structure questions simultaneously. It would tell us definitively whether the Moon is warmer inside than standard models predict, whether the deep moonquakes represent ongoing partial melt activity, whether the shallow moonquakes are associated with the young scarps, and what physical state the core is in today. The technology to do this exists. Modern broadband seismometers are more sensitive and lower power than the Apollo seismometers. The challenge is not technological, but logistical. Delivering and deploying seismometers at multiple locations on the Moon in a coordinated way is a significant mission complexity. Several concepts for a next-generation lunar seismic network have been proposed. The Lunar Geophysical Network concept, developed by NASA's planetary science community, would deploy 4 seismometers at diverse locations, including a far-side station. It has been endorsed by the Planetary Science Decadal Survey as a high priority. Whether it will be implemented as a standalone mission or as part of the Artemis architecture or through commercial delivery remains to be determined. Until such a network is deployed, we will continue working with the Apollo data reanalyzed with ever-improving techniques, supplemented by whatever new seismic measurements individual commercial payloads can provide. The picture will improve, but it will improve slowly, incrementally rather than transformatively, until a comprehensive network is in place. Let us now talk about one more specific and striking aspect of lunar strangeness that deserves its own discussion: the fact that the Moon appears to be losing its exosphere in ways that reveal ongoing surface processes. The Moon has an exosphere, an extremely tenuous envelope of atoms and molecules at the surface, so sparse that the particles rarely collide with each other, and the mean free path is much larger than the exosphere itself. This is not an atmosphere in any conventional sense. The total mass of the lunar exosphere is approximately 10 metric tons, compared to Earth's atmosphere of approximately 5 quadrillion metric tons. The lunar exosphere is more similar to the vacuum of space than to an atmosphere. But the lunar exosphere is not empty. It contains argon, the argon-40, produced by radioactive decay of potassium-40 in the lunar interior and released through outgassing. It contains sodium and potassium, released from surface minerals by solar radiation and micrometeorite impacts. It contains helium-4, delivered by the solar wind and re-released from the surface. It contains molecular oxygen released from surface minerals. It contains trace amounts of many other species. The argon-40 in the exosphere is particularly interesting as evidence of ongoing interior activity. Argon-40, produced by radioactive decay of potassium-40 deep in the lunar interior, must migrate through the solid rock, through grain boundaries and fractures, to reach the surface, where it can be released into the exosphere. This migration takes time, and the flux of argon-40 reaching the surface reflects the porosity and fracture density of the lunar crust, and the rate at which tectonic activity opens new pathways. The LADEE mission, Lunar Atmosphere and Dust Environment Explorer, which operated in lunar orbit from 2013 to 2014, characterized the lunar exosphere in the most detail ever achieved. LADEE's measurements confirmed the presence of argon and characterized its temporal variability. The exospheric argon concentration is not constant, but varies with the lunar day and with specific events. One notable finding was that the argon concentration in the exosphere increased following moonquake events, consistent with the idea that moonquakes open fractures that allow trapped argon to escape more readily. This connection between moonquake activity and exospheric composition is direct evidence for the ongoing geological activity we have been discussing. The Moon's interior is not so thoroughly cooled and solidified that argon produced deep inside cannot find its way out. The cracks and fractures being opened by ongoing tectonic activity are providing the conduits through which interior volatiles reach the surface. The exosphere is a real-time record of what is happening inside. The dust component of the exosphere is also revealing. LAD-D carried a dust detector that found evidence for a thin, sporadic dust cloud around the Moon, particles lofted by micrometeorite impacts and potentially by electrostatic effects. The understanding of this dust population is important for characterizing the hazard environment for future surface operations and for understanding the overall dynamics of material cycling on the lunar surface. The Moon is not passively sitting there being bombarded and slowly cooling. It is actively cycling material, from the interior through outgassing, from the surface through impact lofting and electrostatic levitation, from space through solar wind implantation and meteorite delivery. It is a dynamic system with multiple interacting processes, none of which are completely understood, and all of which are being actively characterized by ongoing research. This is the Moon we are going back to, not the simple dead world of the textbook, but a world with ongoing geological activity, slower than Earth's, but real. A world with water in unexpected places. A world with magnetic memories of an ancient dynamo. A world that shakes, that releases gas, that lofts dust, that occasionally flashes. A world that has been telling us for decades through its data that our models are incomplete. And a world that is waiting, patiently, as planetary bodies do, for us to develop the instruments and the understanding and the presence to finally read what it is telling us, accurately. The science is not finished. The Moon is not solved. The strangeness is not an anomaly to be explained away. It is an invitation to understand more deeply. Something really strange is happening on the Moon. The data says so. And following the data, carefully and honestly, is how we find out what. There is a specific moment that happens when you look at the Moon carefully enough for long enough. Not the casual glance, the instinctive recognition of the familiar face, the dark patches and bright highlands that every human being has looked at for all of recorded history and beyond. Not the intellectual appreciation of what it is, a world, a real world, 3,474 kilometers in diameter, locked in tidal synchrony with Earth, ancient beyond comprehension. But the specific moment when it stops being a familiar object and starts being a genuinely strange one. When you know that the surface you are looking at is not quiet, that moonquakes are occurring right now, deep ones, triggered by the tidal pull of the Earth below the horizon, shallow ones from faults slowly moving as the crust contracts around a cooling interior, magnitude 5.5 events that ring through the dry, fractured rock for up to an hour. That somewhere on that surface, young scarps are forming, geological faults so fresh that almost no craters mark them, evidence that the Moon's circumference has shrunk by 50 meters in the past few 100 million years as the interior cooled and compressed. When you know that in the permanently shadowed craters near the South Pole, invisible from Earth, eternally dark, colder than the surface of Pluto, water ice has been sitting undisturbed for billions of years. That on the sunlit surface, visible to you right now, water molecules exist trapped in tiny glass beads formed by ancient meteorite impacts, protected from the solar ultraviolet that should destroy them, present where all calculations said they could not persist. That the familiar orange glow of some regions visible through a telescope may be partly the consequence of radon gas escaping from the interior. Radioactive argon-40 produced by decaying potassium deep in the lunar mantle, finding its way through fractures opened by moonquakes to reach the surface. When you know that the bright, sinuous swirls, Rhina Gamma and hundreds of others, exist because the rock beneath them is magnetized by an ancient magnetic field from a dynamo that operated 1 billion years ago or more, the frozen magnetic memory of a fluid core that once generated a global field and then slowly ceased, leaving behind only these localized anomalies where the field is preserved in the rock itself. That these magnetic fields partially shield the surface from the solar wind, preventing the space weathering that darkens the surrounding regolith, so that the swirls are bright precisely because they are protected by the ghosts of an ancient magnetic field. When you know that somewhere on the surface, in regions not yet visited by any spacecraft, in small dome-like structures scattered across the Maria, there may be volcanic features as young as 50 to 100 million years old. Not ancient lava, not the 3 billion-year-old basalts of the Mare Plains. Possibly geological children, formed when the dinosaurs were alive, when the continents were in recognizable positions, when mammals were already running across the Earth's surface. If those features are genuinely young, it means the Moon was volcanically active in the era of complex life on Earth. It means we share a geological epoch with the last eruptions of the Moon. The Moon you are looking at is not a museum piece, not a preserved fossil from the early solar system sitting unchanged since the Apollo astronauts left it. It is a slowly changing world with ongoing geological processes, slower than Earth's, quieter than Mars's in its active periods, but real, measurable, recorded in the data from 5 decades of robotic exploration, pointing toward a picture of the Moon that our standard models systematically underestimated. And we do not fully understand why. The heat is higher than predicted. The seismicity is more complex than expected. The water is more widely distributed than believed. The magnetic history lasted longer than modelled. The recent geological activity is more extensive than assumed. Each of these individually might be explicable as a local anomaly or a model adjustment. Together, they suggest something more fundamental, that our understanding of how small, rocky worlds evolve thermally, geologically, and magnetically is incomplete in specific ways that the Moon is exposing. This is the specific discomfort of good science, not the comfortable confirmation that our models are right, the productive discomfort of data that does not quite fit, that is mostly consistent with what we expected, but contains specific, real, reproducible anomalies that honest analysis cannot explain away. The kind of discomfort that historically precedes the theoretical adjustments and new frameworks that eventually transform our understanding. The Moon is producing this discomfort right now. In the pages of planetary science journals, at conferences where researchers compare data and argue about interpretations, in the orbital data coming back from Lunar Reconnaissance Orbiter and the surface data from Chang'e missions, and the ongoing reanalysis of Apollo seismic records with modern algorithms, the Moon is generating productive scientific discomfort on multiple fronts simultaneously. And we are going back. Not with robots alone, though the robots are coming in quantity over the next decade, more diverse missions to more locations than any previous era, but with human beings, with the specific intelligence and adaptability and scientific judgment that human field scientists bring to complex geological environments, with the ability to notice what was not expected, to follow an observation wherever it leads, to exercise the kind of real-time scientific reasoning that cannot be pre-programmed. The first human beings to land near the lunar South Pole will stand in an environment that no instrument has fully characterized. They will be surrounded by permanently shadowed craters that may contain ice, or may contain different concentrations or distributions than current models predict. They will be in the vicinity of young geological features whose age and origin are still debated. They will be in the geologically diverse South Polar region where multiple lines of ongoing activity converge. They will be the first human beings to see this place directly, with human eyes and human perception and human capacity for surprise. What they find may confirm what the orbital data suggests. It may reveal something different, something the orbital data, however good, could not see. This is always the way with human exploration. The first direct encounter with a new environment reveals things that remote observation cannot. And they will report back. Through the same basic physics that has constrained human communication with the Moon since the first missions, the speed of light, the distance, the 2.5-second round-trip delay, they will tell us what they see, what the surface looks like up close, what the permanently shadowed regions reveal when illuminated by artificial light for the first time, whether the water is where the data said it would be, whether the geological features look as young as the crater counts suggest. And then, if we are patient and sustained and serious about this, more missions, more locations, a seismic network finally deployed at multiple locations including the far side, heat flow measurements from diverse geological settings, samples from the South Pole-Aitken basin floor, samples from the potential young volcanic features, gradual, systematic, patient accumulation of the data needed to answer the questions the last 6 decades of exploration have opened. This is how planetary science works at its best, not through single dramatic revelations, but through the patient accumulation of increasingly precise measurements from increasingly diverse locations, interpreted with increasingly sophisticated theoretical frameworks, building toward an understanding that gets progressively closer to the truth. The truth about the Moon is not finished. The Moon we thought we understood, the cold, dead world, the fossil from the early solar system, the solved problem, was a simplification that the data has progressively complicated. The real Moon is stranger, more active, more complex, more interesting. Right now, while you look at it, the moonquakes are happening, the argon is escaping, the scarps are forming, the water is cycling, the dust is lofting at the terminator. The impact flashes are occurring, too brief and too faint to see with the naked eye, but real and recorded by dedicated monitoring programs. The ancient swirls are deflecting the solar wind, just as they have been doing for billions of years. The permanently shadowed craters are holding their ice in eternal darkness a few hundred kilometers from where future astronauts will set up their habitats. The Moon is there, right there, closer to you than any other world, a few light seconds away, a few days' travel. Familiar enough that most people stop seeing it, strange enough that those who look carefully enough cannot stop being surprised by it. Something is happening on the Moon, multiple things, slow things, old things, still playing out on geological timescales. Things we expected and things we did not, things we understand and things we are still working to understand. Go outside and look at it tonight. Let it be strange. Let it be the world it is, rather than the museum piece you might have assumed it was. It is doing things right now. We are just beginning to understand what.